So multiplying and dividing complex numbers in rectangular form can be a little bit complicated. So that's why we use polar form to multiply them, because it's much easier. All you do when you're multiplying two complex numbers together in polar form, if we have our first complex number a equals cis of alpha and our second one b equals cis of beta, all you do is multiply the moduluses of each individual one together, and then you add the arguments. And when you divide the moduluses and subtract the arguments. So I'm going to just walk through a proof of that for the multiplication piece at least. So if you have two numbers in polar form multiplied together, you can pull the moduluses a and b out to the front to just give you cis of alpha, cis of beta. You can expand each of those to cosine of alpha plus I sine of alpha, and cosine of beta plus I sine of beta. Then you factor this out, you get this whole expression. Notice you have a cosine of alpha plus beta and an I squared sine of alpha plus beta, but I squared is just -1, so what you really have here is cosine of alpha, cosine of beta minus sine of alpha, sine of beta, which you should recognize as cosine of alpha plus beta. And then this middle section here, you can factor out an I and rearrange it. You have sine of alpha cosine of beta plus sine of beta cosine of alpha, which is your sine of alpha plus beta, with the I on the front. That simplifies to cis of alpha plus beta, and that is our proof for this identity. So to put that into practice, we have two complex numbers, z sub 1 and z sub 2, and we want to find z sub 1 times z sub 2. So all we have to do is multiply the moduluses together, and then inside the cis we add the arguments, and this tells us that z sub 1, z sub 2 is equal to 6 cis of 3 pi over 4. And that is how you multiply and divide complex numbers in polar form.